Okay, let's talk about past climate changes as well, because we've just seen what's going on now, but we want to know how much has Earth's climate changed in the past? Do we need to worry about 1 Celsius of warming, or 2 Celsius, or 5 Celsius? We'll look at changes over Phanerozoic time, right? So that's since the start of the Cambrian, since we had multicellular life with hard parts, since we had fossils, basically, the past 550 million years. We'll look at one example of climate changes that are almost as fast as we're doing today, but even the most rapid natural changes that we have to look at during this Paleocene-Eocene thermal maximum are probably a little bit slower than we see going on today, which is pretty frightening. We'll look at ice ages, what's caused those and the rates of change and the magnitudes of change during those, and an event called the Younger Dryas that people tend to mention when it comes to climate change on Earth. We'll also talk about the Little Ice Age a little bit. Some folks will say that all of our warming has just been coming out of the Little Ice Age, so everything's fine. I will disagree with that. Then we can talk about some multi-year cycles in oceanic heat, things like El Nino that you've probably heard about, and then the impact of volcanic eruptions. So here are our Phanerozoic, climate changes, so over the past 550 million years. And notice that the changes in time scale on the bottom. This is not an even time, so this is 400 million years there. And then this is since the dinosaurs died off. And then this is the past 5 million years to 1 million years ago. And this is all the past 1 million years here. If we look at the scale of changes over Earth's history, from its hottest, they're probably Cambrian and the Paleocene thermal maximum, to its lowest, around now, or around the Permian, that scale of change is about 20 Celsius. So Earth's climate has only changed since animals were really a thing by about 20 Celsius. So if we're talking about changing 5 Celsius, it's a pretty substantial part of that. It's pretty unimaginable that we would be able to have enough fossil fuel to burn to push us past that limit. So that's not the worry here. The worry here is just that the magnitude of change that we can cause is significant enough to have a real large impact. Let's focus on what we call the PETM, the Paleocene-Eocene thermal maximum, which is this spike in temperature right around the Paleocene-Eocene. Those are periods during the Cenozoic, right? Some changes that happened back then. That was rapid climate change, maybe analogous to today. More warming than we've seen so far, 5 to 8 Celsius of it, probably due to extensive volcanism that wasn't releasing as much soot, but was releasing a lot of greenhouse gases. So over 10 to 50,000 years, right? And so that's several degrees of warming over 10,000 years. Today, we've got, 1 degree of warming so far up to, like 5 degrees or some of the high-end estimates over a couple hundred years. So the rate of change during the PETM we still think was slower than today. The magnitude of change was bigger, but the rate of change was still smaller than what we see today. This is still a thing a time period that we study for evidence of this. And what we see was that during the PETM, there's a mass extinction in marine fauna, and that there were huge ecological changes over all sorts of different biomes. One of them actually being the rapid spread of primates. So, go us, that helped us out a little bit, at least our ancestors. Just want to point out that the PETM is commonly studied as an analog, as a similar time period for today because of how fast climate change back then. And it's still not as fast as we're seeing today. Let's expand that a little bit and look at glaciation. So glaciation, we're talking about what has happened since the Antarctic ice sheet just started to form, which was around here. So it started to form around when the temperature was about 7 degrees Celsius warmer than today. That was involved with about 300 feet of sea level drop. Conversely, If we happen to increase the temperature up to about 7 Celsius, which is at the very upper bounds of what we think we could do with current models, if we burn it all, we drill, baby, drill all the way home, then we could increase it by about 7 degrees Celsius. Eventually, that would probably cause the whole Antarctic ice sheet to melt, and we'd have 300 feet of sea level rise, 300 feet, if not more. We would start to see major melting above about 4 degrees above today. In addition, so this is roughly when Greenland started to form, right? There was a cold period that started to form at about 3 million years ago. And so, at most, the Greenland ice sheet has existed when it was about 3 Celsius warmer than today. That means that if we do 3 Celsius of warming, which is well within the bounds that we could do, we're probably headed there if we don't change anything, that we're not going to have any Greenland ice sheet. That's going to cause about 20 feet of sea level rise. It's not going to flood Knoxville, but it's going to flood New Orleans and New York and Miami and every other coastal city in the world. So that's where the big danger is. And it's not all going to happen at once. I'll say that too. Even if we warm 3 Celsius by 2100, the ice is not going to melt right away. But 2300 by 2400 probably will. You'll see a lot of melting that starts to happen, in our lifetimes. So that's the hazard here, that looking at our past, that 3 Celsius of warming is associated with changes big enough to melt the entire Greenland ice sheet. So when you say, what does 1 degree matter? What do 2 degrees matter? What do 3 degrees matter? That's what it matters. It's a big impact in Earth's history. But let's look at the ice ages too. So, over the past few million years, especially the past million years when we have a good record of ice cores. Remember, we talked about how these are initiated by Milankovitch cycles, but then there are feedbacks involving greenhouse gases and albedo, ice sheet reflecting light, that really are what drive most of that warming or cooling. So, right, cycles of warming and cooling associated with the shrinking and growth of those ice sheets. Probably the last time that it was warmer than now at Earth's surface was not millions of years ago. It was during the Eemian. So that's about 120,000 years ago. It's the last time that we reliably think that was probably a little bit warmer than today still. Carbon dioxide was at 280 ppm. Right now it's above 400. And that just means that there are probably some either, there's going to be a lot more warming to happen just as a result of what we emitted, or that there were other forcings going on during the Eemian as well. But I want to point out that sea level during the Eemian was 20 to 30 feet higher than now. And West Antarctica, so part of Antarctica lightly had melted, which had added 8 feet of sea level rise in a century, right? We said, okay, we've seen about 9 inches so far. Well, imagine if we saw 8 feet. That's a possibility. So the Younger Dryas, which is labeled here in YD, that was a time period of sudden cooling in the middle of us warming out of the last ice age, right? So like 13,000 years ago, it sort of suddenly cooled again, at least in part of the world, really only affected the northern hemisphere. What we think happened there was a huge freshwater dump from the ice sheet as it melted, right? So think of Canada, its ice sheet is starting to melt and it's dumping a ton of fresh water into the northern Atlantic. And we had looked at that current that was called the North Atlantic Current or the Gulf Stream. Well, if you dump a bunch of fresh water on top of that, it's actually going to stop that current from moving. And as a result, there's less heat being brought northward toward Europe. So you can actually get a huge cooling in Europe, even as the rest of the climate continues to warm. Weird that warming could cause local severe cooling, but I wanted to point out that that's a thing that could happen. It's not all warming all the time, everywhere. Lastly, I wanted to point out this medieval warm period and this little ice age that get brought up, which are these relatively small variations of a couple tenths of degrees that we see in Earth's history, especially in records from Europe. We think that the Little Ice Age was this few hundred-year period of colder temperatures, primarily in Europe, so it was pretty regional. There could have been all sorts of forcings that played a part. Orbital would be things like Milankovitch cycles, volcanic forcings, extra aerosols introduced, solar forcings. So these are all things that we weren't causing. during the 14, 15, 1600s. It may have all played a part, but we can see that today's warming that's gone up, to here and beyond, that's not all recovery from the little ice age. Maybe we hit that around the year 1940 or 1950, but since then we've kept warming and much faster. So the medieval warm period, to the best of our knowledge, was not warmer than today.